This video explores the paradox of X-ray ghost imaging, focusing on decoupling resolution from radiation exposure to capture perfect diagnostics with microscopic risk. Traditional X-rays use a brute force approach, known as the straight-through current paradigm, where a dense beam of photons passes through the subject to a sensor. This quest for high resolution has a high biological cost due to ionizing radiation. X-rays carry enough energy to damage DNA and increase cancer risks by knocking electrons out of atoms. X-ray ghost imaging is a complete departure from straight-line photon exposure. It adapts visible light techniques to the X-ray spectrum to decouple image resolution from patient exposure. Step 1 is the split, where a specialized crystal beam splitter separates a primary X-ray into two identical correlated beams, both sharing a highly specific, random speckle pattern. Step 2 is the patient path, or path A, where an extremely weak X-ray beam is directed at the patient or biological sample, ensuring minimal radiation exposure. A bucket detector is positioned behind the patient. This single pixel detector cannot form an image. Its only function is to count the total amount of light or faint flashes that pass through the body. Step 3 is the camera path, or path B. The second, identical beam is routed away from the patient and shines directly onto a high-resolution, multi-pixel digital camera to capture high-resolution data without patient exposure. The system operates with two correlated paths simultaneously: Path A, with low data and low exposure for the patient, and Path B, with high data and zero exposure for the camera. Step 4 is the computational ghost. The bucket detector registers a drop in intensity as X-rays hit dense tissue. A computer then records the exact speckle pattern hitting the high-res camera at that precise microsecond. By correlating thousands of these flashes, the computer mathematically builds the patient's internal image. The final, high-resolution ghost image is constructed exclusively from the data of the second beam that never touched the patient. The process is low dose because the bucket detector doesn't need to resolve an image. It only needs to detect faint flashes of total intensity, allowing the patient beam to be incredibly weak. Advanced algorithms, referred to as the software multiplier, supercharge the physical setup. Compressed sensing and deep learning enable perfect image reconstruction from a microscopic fraction of raw data. This technique allows for perfect image reconstruction using less than 25% of the X-ray photons used in a traditional CT scan or X-ray. X-ray ghost imaging offers maximum resolution with microscopic radiation, drastically reducing the risk of cellular damage. The future of medical imaging relies on computation, not brute force exposure.